All right. Good afternoon, everyone. We're gonna get started. Happy to see good audience today for two local speakers of the AstroAI lunch seminar. The first one is Sofia Uzsoy, who is a grad student here and who's actually speaking for a second time this semester, I believe. Or no, last semester. Sorry. I guess she should be great. She gets many ideas all the time. So she's gonna be telling us today about a project she submitted to NERIPS, working with a couple of people there and Melanie on manifold learning from cosmic structures, which is something about how is an efficient way to learn the different types of structures that you see in the cosmic web. And then we'll have Mike Smith, AstroAI fellow, that I'll introduce him. Let's get started. Thank you, Sofia.
Great. All right. Well, thank you so much for having me. Like Rafael said, my name is Sofia, and I'm a PhD student here. I'm in my 4th year, and I work with Finetuned. But this is something else that I did, working mostly with Melanie Weber, who is a professor in the applied math department. But I actually took her class, which was called Geometric Methods for Machine Learning. A little like a year and a half ago, I took her class, and then this is something that kind of came out of my final project for that class. So yeah, excited to talk to you about it. Feel free to interrupt if you have any questions. Okay. So how do we probe cosmic structures? And what I mean by cosmic structures are things like clusters, filaments, nodes, etc. Right? And these are ways that we can characterize the large-scale structure of the universe. There's a lot of things that we're interested in that. Like we're interested in how the properties of galaxies in these different kinds of structures differ and why. And we're also interested in how we can probe the evolution of these kinds of structures over like redshift, over cosmic time, right? And so there are a lot of methods already to identify these kinds of structures. The current ones, a lot of people use clustering algorithms, right? Like k-nearest neighbors and dbScan, and there's a friends of friends clustering algorithm. And these are algorithms just to identify clusters. So they're like binary. They're like yes or no, 0, 1, this is in a cluster, or this is not. And so they're discretized in that way. But they don't capture any nuances. They don't capture things that are like, for example, in filaments or that are potentially on the outside versus inside of clusters. They don't capture that. But they are very fast, actually, and often they can be accurate in identifying clustering structures. The next method is local density estimation, right? Where people will draw like basically a sphere of a given radius and they'll count how many galaxies are in that sphere. And that is good because it is continuous, right? And so I see a lot of papers where they will plot different galaxy properties as a function of the local density. And that's great because you can plot it against things, but it doesn't include the actual structure of environments, right? Like it doesn't take into account the distribution of those galaxies within that radius. So we're losing information there. And then the third way that people characterize these kinds of structures are using the eigenvectors and eigenvalues of the Protection matrix. So for every galaxy, they can calculate the Protection matrix and do an eigendecomposition, and then using the eigenvalues, they can classify things as being in nodes, clusters, filaments, sheets, points, etc. And that is very detailed. That gives you all the second order information that you want. But it's very computationally expensive to do this kind of matrix calculations and conversion for every galaxy if we have a huge data set, right? And so the thing here is that 3D galaxy maps are getting huge. So this is DESI, which has tens of millions of galaxies, with surveys like DESI and LSST, where we're going to have millions and millions of galaxy positions, and we want to be able to characterize these kinds of structures on really large scales. And so it is really important to have a method for characterizing these structures that's not only continuous and nuanced, right? That we can plot against things, that captures like details of structure, but we also really need it to be very scalable, right? So that we can scale it up to these really, really massive figures. Okay. So my argument is that we do not currently have a method that is both continuous, nuanced, and scalable. And so what I'm proposing is a method that what we really want as an input, we wanted to take in a 3D point cloud. So just like galaxies, positions of galaxies, and we wanted to output a low dimensional, preferably one dimensional, representation of the surrounding structures of these galaxies. So we want like a low dimensional embedding space that is going to represent the geometry and the structure of local environments for galaxies in very large data sets. That is both continuous, nuanced, and scalable. Okay, so that's what we're trying to do here. And so while I was developing this method, I realized very quickly that I actually need to make sure that it works in ways that I understand. And so first I developed this toy data set, which is very simple. This is a 20 by 20 by 20 box. and I have two balls of points that I sample from like a 3D Gaussian distribution, and then I connect them with the line of points. So each of these balls has 1,000 points. The line has, or each ball has 500 points. The line has 200 points. And then I take 1,000 points and I like randomly scatter them like uniformly throughout the box. And so my first challenge is with this toy data set to create a method that can separate out the balls from the line from the randomly sampled points. Okay, so this is what we're going to try to do. And so now I will talk to you about the actual method and how it works. So an overview of the method, and if you guys know a method called ISOMAP, which is another manifold learning method, this is actually pretty similar to that. But the idea is first that we're going to define a neighborhood radius as if we're doing local density estimation. This neighborhood radius is the scale of the structure that we're trying to capture. Okay. And then we're going to calculate the physical distances between galaxies within a radius. So by physical distance, I mean, we're going to use Euclidean distances in X, Y, and Z, but only for galaxies within a radius. And we're going to set the distances to all the galaxies outside of the radius to 0. So for every galaxy, we calculate the distance to their nearest neighbors within that radius, and we set all the other galaxies to 0. And so when we do that, we get, for this toy data set, we get a distance matrix that looks like this. Okay, so this is a matrix of 2200 by 2200, because that's the number of points in my toy data set. And then you can see very clearly the different structures that I have, right? Like these two like squares are the balls, right? Because they have a lot of neighbors. This line is the line, and then all of these other points are the randomly scattered points that really don't have that many defined neighbors. And so then all of these, the rest of the entries in this matrix are in purple. They mean they're 0 because they're outside of my distance radius. Okay. So first we just do this like pairwise Euclidean distances within the radius, and then here's where the trick comes in, because we don't want to necessarily reproduce just the locations. We want to capture the neighborhood, the geometry of the neighborhood. So then the next step is we're going to take these distance vectors. So this is a distance matrix, which is symmetric. You can think of every like row as like a distance vector. Like for every one galaxy, every row is its distance to every other galaxy in the data. Okay. And then what we're going to do is we're going to take this matrix and we're going to sort it along the x-axis. So we're going to sort all of the galaxies. For one galaxy, we're going to sort its distance to all the other galaxies. And what we get there is a matrix that's vast majority 0, except right at the end, where we're going to have all the like defined distances. And so then every galaxy has a sorted vector of the nearest neighbors. And then what we're going to do here is we're going to take this sorted distance matrix and we're going to calculate another distance matrix. We're going to calculate Euclidean distances between sorted distance vectors. So these are not physical distances anymore. What we're doing by calculating Euclidean distances in this sorted vector space is we're calculating similarity distances between every galaxy's neighborhood, right? So for example, one galaxy has some neighbors that are like 1, 3, and 5 megaparsecs away. We're going to sort that and we're going to compare it to galaxy 2, which has galaxies at 2, 4, and 8 megaparsecs. We're going to calculate the Euclidean distance between those big vectors. And that's going to give us one value that's going to tell us how similar is the neighborhood of galaxy 1 to galaxy 2. So a galaxy with very low similarity distance means that they are very similar. They have very similar neighborhoods. Galaxies with a very large similarity distance means that they're very different. Okay. So this is going to tell us like how similar galaxy 1's neighborhood is to galaxy 2. And we're going to do that for all of the galaxies in our data set. Okay, so now we have a new distance matrix of our similarity distances. And then we're going to move on to the next step. But are there any questions just about the procedure that I've outlined so far? Yes.
So at step 4, this is a Euclidean distance in a 2000 something dimensional space.
Correct. Yeah, correct. Exactly. Yeah. Yes.
Does it need to be Euclidean distances? Could you
Nope.
just as well do non-Euclidean?
Yeah, you could do anything. I thought about doing cosine similarity, but I decided on Euclidean distance because it's simple, but you could do anything. For like the physical distances, you want to think about how to do that differently from the similarity distances because there's different ways to do both of those. But I chose to use Euclidean for both, but they don't.
What is the impact on which metric distance you use on the actual results? Is there a way one for the actual galaxy maps? You would prefer a cosine similarity versus simply Euclidean, or
That's a good question. The honest truth is that I haven't tried other ones.
Wow.
But these are things to think about. For example, like I'm doing this on a toy data set of points that I made. Later, I'll talk about how I do this for the TNG simulations. But you have to think about the size. If you're using like galaxy simulations or real data, you want to think about like cosmological distances, right? And if you need to take into account other things, or if you can use like a locally linear approximation that I'm doing, right? But yeah, I could do this with cosine similarity or another distance vector. I don't think it would change that much, but I haven't tried it. Yep.
Can you also fold in uncertainties on these in like some type of weighting scheme on the distances? So you can, yeah, just like math folds and.
You could, yeah, so you can define your distance metric in any way. I can envision, for example, a way that you would, if all of these are galaxies with properties, you could weight galaxies with similar or more different properties differently. For example, if you wanted to calculate that kind of distance. But there's a lot of room here, wiggle room for how you want to define your distance metrics according with what you were looking for, basically. Any more questions? Okay, let's keep going. So now I have this distance matrix of similarity distances, and then we're going to move on to the next step, which is we're going to put this into a method that already exists. It's called multidimensional scaling, and I will talk about it. Okay, so multidimensional scaling is a nonlinear dimensionality reduction technique that is well known. I did not make it up. The idea is that if you have some number of points n, you want a low dimensional embedding of those points, a low dimensional representation that preserves the distances between points. So this is a method where you take in a distance matrix of any kind of distance, and it gives you a low dimensional embedding that preserves the distances between points in this low dimensional space as much as it can. Okay, so your input matrix is a symmetric distance matrix, an n by n matrix, where n is your number of points. And your output is an n by n representation, where m is the dimensionality, m is much, much lower than n, right? So you want to take all these points and compress them all to a very low dimension space. And I will quickly go over, I wrote out all the math of how this works. It is actually, I consider, very intuitive. I'll go over it quickly, but please let me know if you have any questions. So the way this works is you have a distance matrix, D, this is your input. First, you calculate this centering matrix, which is the identity minus 1 over n times a matrix of ones. And then you apply the centering matrix on both sides of the distance matrix like this. And really all you're doing is you're getting another matrix that takes this distance matrix and is centering it along both dimensions. It's subtracting out the mean so that it is like centered at 0. That's all you're doing. And then you take this new centered matrix and you do like an eigendecomposition just like it's PCA. And then your low dimensional embedding is this X, which is all the eigenvectors scaled by the square root of your eigenvalues. And then you can take the top however many dimensions that you want to take. Sorry for the people in the back, that's kind of low. But this is actually very similar to PCA, right? The only difference is that you pass in a distance matrix and it doesn't have to be any sort of like physical distance, like it's similarity distances. But the idea is very similar. You just take this distance matrix, you center it along both dimensions at 0, and then you basically do a PCA and you take the top small number of components. And that's your representation. Any questions about that?
Sorry, why not use PCI instead?
Well, PCA just works on like a data-driven covariance matrix, right? The idea is we're doing the same kind of eigendecomposition, but on a distance matrix, like a matrix of distance, right? It's not like a covariance matrix of the data. And so it's not going to give you back principal components of the data, right? Instead, this is giving you a low dimensional, like in PCA, you take the top small number of components. Here we take the top small number of components, but instead we're conserving the distances. So PCA takes in a covariance matrix and is preserving the variance as much as it can. Here we're giving it a matrix of distances, and we're saying, give me a low dimensional representation such that the distances are as best preserved as possible. That's the difference.
Does UMAP present distances?
UMAP does, but it also has some other constraints. We were talking about this actually at the AstroAI meeting. I don't really remember the constraints, but it has some additional constraints. So this is like a linear decomposition where UMAP is not necessarily that. Okay. We also talked about it in relation to TC, which is also.
Which does not present distances.
Yes. Yeah. Okay. Any more questions? So we put it through this method. Let's go back. We have my toy data set with my 2 balls, the line, and these uniformly distributed points. I'm going to put them through this method, and now it looks like this. So we're basically here, I'm coloring every point by the first embedding dimension. And so you can see that in this embedding space, the balls are a different color from the line, which are a different color from the uniformly distributed points. So that's the idea, is that we're unsupervised and automatically able to separate out points based on their surrounding structures in their local geometry. Okay. And something else that I think is interesting is, even just aside from like looking at this, if I plot all the points in the top 2 embedding dimensions, it looks like this. But because I made the data set and I know which point belongs to exactly which structure, I can go back and color the points by the structures that they're in, and then I can see how they can separate, right? So these pink points are the line, the points that are in the line connecting 2 balls. These red points are the randomly distributed points. And then I separated out the points according to which ball they're in. So they're like orange and blue points are in the different balls. And I think it's very important, first of all, that these cluster according to their structure, right? All the points in the line are down here. All the randomly distributed points are up here, and then the points in the balls are in the middle. But specifically, you can't tell which ball is which. And that's important, right? Because we don't want any positional dependence in this embedding. We want it only to encapsulate the geometry of the local surrounding neighborhood. And so from this perspective, the two balls are different, but they have the same geometry. And so we want them to be indistinguishable in embedding space. And so it's good that they are. And we also see that the points in the two balls kind of span the location of the line to the location of the random points. And that makes sense because I made these as 3D Gaussian distributions, which are going to be more clustered in the center and become like less and like more sparse as we go out. And so we're going to span the like clusteriness of the line to the randomly distributed points. And so we see all of this in the top two embedding dimensions, which makes me feel like we're actually capturing what we want to. Does that make sense? Are there any questions about this?
So the region occupied by the line embeddings, purple.
Yeah.
Seems to also include a little bit of both, right? I mean, I guess that's expected because I guess you don't kind of really distinguish between parts of it, but it's
Sorry, a little bit of both.
so it's overlap.
Sure.
Overlaid on
Yeah.
some orange and blue points.
Totally, yeah.
Is that just basically because there's some regions of that line that are
Well, the lines actually do go right through the center of both balls. I did that by design. But also we would expect that the points in the center of the balls, right, are gonna approach the same like concentration as the points in the line. And so we see that some of the points in the ball overlap with the points in the line, and some of them overlap with the randomly distributed points. But the idea is that through this continuous embedding, we're able to see the evolution and the nuance between that instead of just being like 1-0 cluster or not. That's one of the benefits of this. Any more questions?
Do you know how much of the embedding is capsulated in these two dimensions?
Yeah, so you can do basically the same thing that people do with the PCA, right? Where you use the like eigenvalues to tell you basically the conserved variance or like the amount of distance conserved, I guess. I did see that it goes past 95 when you go up to the top 5.
Okay.
But obviously like the first one conserves the most and the second one conserves the second most and so on. Yeah. Anything else? Okay, let's keep going. So this is all fine for this toy data set that I'm in. Oh, one other thing that I wanted to talk about is this distance, the like radius that I'm using is actually, that's a hyperparameter, right? That you can do. Like I decided on the radius that I'm considering the neighbors in between. And so one of the things, this paper got accepted to the NERSC conference. One of the things that one of the reviewers brought up was they were interested to see how I chose the radius and what it looks like with different radii. And so I went back and I made a bunch of plots that I thought might interest you. So the radius that I used for these two plots is a radius of 0.5. So then I went and did the same pipeline again, but with a bunch of different radii. So first I use a radius of 0.1, which is too small, right? And you can see that first of all the points in the balls look the same as the uniformly distributed points, and it picks up the line, but nothing else. And you can see that actually this looks really bad because all the points in the line have the exact same value, and all the randomly distributed points have the exact same value. We're not able to distinguish the nuances there. So this is too small. This is the the value that I actually used that I showed you, which I think captures the best amount, the most amount of the structure that we're interested in. But then we can go, I ran it again with R equals 1, and you can see that things are starting to get more spread out here, and you can't, like, the random points are starting to bleed too much into the balls, and the line points are bleeding too much into it, and you can't really tell them apart in this embedding space. You still can kind of, like it's still doing okay. And then as I go to higher and higher dimensions, we're seeing that we're able to distinguish the different kinds of structures even less. And so I took this absurdly high to a radius of 5, and finally a radius of 10, and you really can't distinguish the like structures that I'm interested in. So I guess to set the hyperparameter, you kind of have to know the rough size of the structures that you're looking for. Although in practice, you could automatically pick the radius, for example, by looking at your distance matrix and being like, I only want to capture a third of the data set or something like that. You can use that as a rule of thumb to set your radius. So that's an idea, but yeah, this is how I selected the cutoff radius. Okay, so that was all on a toy data set that I made with some points and balls and lines. But where's the actual astrophysics application? So we have the illustrious TNG simulations, which give you a 3D point cloud of galaxies. So this is TNG 100. And this is the data set after I make some cuts on like number of stellar particles and mass and so on. And here I've really like pulled the alpha so that you can really see the overdensities and the clusters and filaments in the data set. And so when I run this through the pipeline, I get something that looks like this, which you can see that the darker colors kind of show more clustery regions, and then as we go to these like purple pink values, we can see that that's kind of tracing more filaments. And then as we get to the yellow values, that's going to be the more uniformly distributed or points in underdense regions. But the good thing is that we don't have to just look at this to see how good it's doing, because all of these points, right, in the TNG simulations are galaxies that have associated properties. And so we can look at that. So this is a plot of the first embedding dimension, which is on the x-axis, and it's going from more to less clustered. So on the left side are the lower values, and that's going to be these dark purple values here, and it's going to less clustered on the right. And then we can plot this as a function of physical properties of the galaxies in simulations, right? So here, I did this as like a twin y-axis because the NERVS papers are only max 4 pages. But on the left y-axis, you can see star formation rate, that's in blue, and then on the right, you can see the halo mass in orange. And we can see that actually, we can pull out things that we know from physical like relationships just from this embedding dimension, right? Because we know that galaxies in clusters are usually more massive and less star forming, they're redder and they're quenched, and we know that this is a redshift 0, by the way, that's important. Galaxies that are less clusters, like field galaxies, are usually younger, less massive, and more star forming. And so we can see that as we correlate these galaxy properties with our embedding dimension, we see that we're actually able to pull out these physical relationships that we know are true. But not only that, we're able to actually capture nuances as we transition from galaxy to field, right? For example, there's this region here from -3 to -1, where both of them kind of stagnate. They don't really increase or decrease. And if we look back at this, if we look at -3 to -1, that's this purplish pinkish region, and that kind of corresponds to galaxies and filaments, right? And so we can see how these galaxy properties transition with the structures. So we can know like clusters, but then we see as filaments, they're not really changing. And as we go back to the field galaxies, then we see them go to the values that we expect. So with this continuous embedding dimension, we're able to capture kind of the in-between nuances, right, between galaxy and field, and we don't have to kind of slice and dice things so cleanly. So yeah, that's exciting.
There's a online question.
Yep.
Okay, so Vinay was wondering, I
Oh,
don't
Vinay.
understand why the representation changed so much. With R, if you had a distance measure that scaled with R, say like a Mahalanobis.
Mahalanobis
Yeah,
distance, yeah.
Mahalanobis distance, there should be no change at all, correct?
If you had a distance metric that changed with R, yes, I would say that's correct. Because all the things that I showed are just using Euclidean distance, and I'm only using the R to make a cutoff when I'm making the distance matrix, right? So any distance larger than that R, I'm setting to 0, right? If you use a distance metric, that's a metric that depends on R, then that's going to change which values are set to 0 or not. Presumably, if I did that, then I would not be setting anything to 0. It would all be dependent on the distance metric. And so that could actually be an interesting way of doing it. Yeah, I would agree with that. Okay, are there any questions about this?
So the fact that you're sort of able to sort of predict some quantities here, like the star formation rate,
Mhm.
what that's really telling you is that your embedding is a good summary of the geometry of the
Yeah.
distribution of these galaxies, but what's dictating the physics about individual galaxies is precisely where in that sort of web they live, you know, whether they live in clusters or in filaments.
Sure, I mean,
Right, it's kind of an indirect connection.
yes, I would not say that the star formation increases because they are in field versus cluster regions. I would not say that's like our causation, but I'm saying that this is a way to quantify what we know. Like from in the past, just looking at 0, 1 in cluster or not, people noticed that at redshift 0, clusters are more massive and less star forming. But we're able to see this in a continuous way that we can quantify and fit a function to if you want, basically by using this method. That's the idea. Okay. The other thing that I did was compared to dbScan, which is like a regular clustering 0, 1 binary clustering method that a lot of people use. So I passed in the TNG 100 dataset, and I did not tell it how many clusters to make. It identified 21 clusters. Here, all of them are colored in different colors. And then I can take the TNG 100 galaxies plotted in the top two embedding dimensions for my method, and then I colored all the ones orange that are identified to be in clusters from DB-scan. And so what you can see is that all of those DB-scan identified cluster galaxies fall into the same region of embedding space, and so I could potentially recover this by just like making a cut in my first embedding dimension. So this shows that not only does it actually encapsulate all the things from traditional clustering methods, it provides a lot more nuance instead of just binary classification. But this was an important sanity check for me. So yeah, that was pretty much all I had. I think this method has some pros and cons. So the pros is that it is continuous and not discretized, as I said, right? And the comparison of distributions of galaxies in the neighborhood allows for more nuances of the neighborhood structures, right, than just local density estimation. And it is extremely scalable because we actually only need to invert one matrix to encode an entire data set, right? And that has significant speedups compared to a method like calculating the Hessian at every galaxy, right? And having to invert matrices potentially millions of times for these very high dimensional, for these very big data sets. The cons are, first of all, it only captures radial distances, right? Because I'm calculating the Euclidean distances from each one. It's only looking at radial distances and it's losing any angular information. So I've made this diagram with these dots to kind of illustrate what I mean. So if we're looking at this black galaxy, right, and we're looking at the distribution of galaxies around it, this method would see this structure as exactly the same as this, right? Where the galaxies are the same distances away, the Euclidean distances are the same, but they're distributed like angularly differently. My method would see these two as the same, which is unideal, certainly, but that's the kind of the trade-off that we're making to be very fast. So yeah, it is very scalable and captures nuances, but it is not as detailed as the Hessian, right? The Hessian is guaranteed to get you all that second order information that is going to let you like definitively categorize things into different structures. And we don't have all of that information, but the argument is that we can get at least some of the most relevant amount of second order information in this very scalable and fast way. So that's the idea. That was all I had. I'm happy to take any questions and thank you for listening.
Okay, maybe one quick one. Yeah.
So when you go back to your DB scan comparison, it seems like the first dimension is capturing something like the density, the local density.
Yeah.
Have you investigated what the second and third and so on dimensions kind of correlate to in terms of some kind of features?
Yeah, that's a great question. And this is also something that the reviewers asked. And the truth is that no, I have not really taken a lot of time to look into that, but I would love to know. It's kind of hard to just look at this embedding dimension and kind of try to intuit physically what it means. And I could take it and I could correlate it with like the average distance nearest neighbors and things like that and try to figure it out. That's something I definitely want to do. But part of the idea is that in order to encapsulate the most information, we are kind of losing out on this aspect of like physical representation and interpretability, right? Because we could plot it as a function of things we already know. The idea is that this is one value that potentially captures more than that, but on the flip side could be less interpretable. But this is something I want to spend my time. Yeah.
Okay. Sofia is not very far, so if anyone wants to talk to her,
This is an eagle win.
yeah, go find her. Thank you so much.
Thanks a lot.
Thank you. And for the second talk today, we have Mike Smith, who is also welcome to us. Mike has recently joined CFA as an astronautic. He did his PhD in the University of Hertfordshire in the UK. Spent some time in Canada, the Turing Institute, and then made a little incursion into industry, learning about how to apply data metrics to space sciences. But we've managed to rescue him from the industry and bring him back to academia. And now he's an AstroAI fellow, and he's gonna be telling us about multimodal learning and his experiments with different types of way of dealing with multimodal data sets. And in particular, maybe he will introduce us to his AstroPT model that deals with multimodality in the context of galaxy science and that's interest, and hopefully he'll get this presentation in the screen at some point. Maybe it's there.
There we go.
There. All right, take it away, Mike. Thank you so much.
There we go. That works too. So yeah, I'm Mike Smith. I am
like Raphael said, one of the incoming AstroAI fellows along with Dan. And today I'm going to be talking a little bit about multimodal models and why text isn't all you need, and different ways that we can imbue like astronomical knowledge into these large models. And this is a talk I gave at the Platonic this summer, extended it a little bit with some new work. So we'll see how long we get, because I've got half an hour, but like I'm hopefully going to be talking to you about 3 different models today. Just as a refresher, for those in the room that just so we're all on the same page, I'm going to be talking about GPT models here. And this is a autoregressive large transform model, the thing behind ChatGPT, Anthropic's Claude, and all these other large models. And what they do to train them is they just predict the next item in a sequence. And this can be a sentence, it can be a set of time series, or just a bunch of chunks, and you're trying to predict the next chunk. And in doing this, you need to learn something about the sequences you feed it. So with this text, it needs to learn that a galaxy might have 5 paradigms. We need to learn something physical about a galaxy. And you can imagine for a time series, if you have a time series of a field seen as a satellite, you need to learn something about crop health and how the crops will react to certain things. But this very simple method of just predicting the next item in the sequence can give these models a lot of knowledge. So how do we make them multimodal? There's really 2 parts here, and there is a reason I picked this meme and not a different one. This is a very important thing to keep in mind. So there's 2 paths, and you end up at the same place, right? There's 2 different paths you can go. You can use early fusion or late fusion, and I'm going to be talking a little bit about what they are right now. So late fusion is when you have 2 different neural networks, or a bunch of different neural networks, all for different modalities. So you can imagine the blue dots there are taking in text, the green dots are taking in images, and the yellow dots are just like the LLM backbone that we just saw with the time series, or the words going in. But the important thing is the modalities go in and they don't interact with each other. There's 2 different paths, they go into the LLM, and then it's recursive. And early fusion is when you pass everything in from the start as a unified thing. So you pass in the text and images all mixed up, you try and predict the next image token for the next text token, etc. And you just let the neural network figure out what's going on. You don't put your knowledge in the network, you don't say, I know best about images, so I'm going to put this image encoder here, I know best about text, I'm going to put the text encoder here. Just let the network figure it out. And I've put a bunch of examples there. I'll be talking a little bit about AstroLLaVA. Yeah, go ahead.
So how do you input here the 2 modalities while keeping the sequentiality? Like how is it going to know whether it needs for the text or image next?
So there's a few ways you can do that. You can just project it directly on the embedding space and then have a sorting token, say a special token that says now it's image time. Then you have a bunch of image tokens, and then you would output now it's text time on the text tokens, and you could decode it using this knowledge. Or you could have the different modalities and push it in yourself to say, no, I want to produce text or imagery. And sorry, I should have said, please shout out if you have any questions at any point. So yeah, there's a few different ways you can do that. I think the most elegant way is to have the special tokens per modality. So you have the text token that goes in a bunch of text, and it produces an image token, which the encoder for the image token. There's some examples. There's LLaVA and Flamingo, which are 2 different models. LLaVA from which we're going to be talking about in a second, an astronomical LLaVA. And on the right, we have Chameleon and AIM, and we're going to be talking a little bit in a little while about AstroPT, which is an AIM-like model for autoregression. But the interesting thing about these 2 approaches that I saw earlier this year in the summer when I was making the first set of slides for this is that it doesn't really matter which one you choose. If you have a set flop budget, say you have 10 to the 21 flops to train a big model, you can pick an early fusion model, you can pick a late fusion model, and they're going to perform similarly well to your flop budget. And I found that quite surprising. I thought maybe the early fusion was going to do better because we're not living around with it so much, so it's going to find the most optimal path. And it turns out it's not the case. This is a paper that was in ICLR, I think, or NeurIPS, one of the big conferences. And they found that early and late fusion models perform similarly well, but it's the same block budget. There are some trade-offs. Early fusion models can encode more information in a smaller package, less parameters. So if your computer is going to be inference heavy, you want to pick an early fusion model because you're going to be deploying it and running inference, and that's going to be more expensive with a heavier model. But if you want to take an off-the-shelf LLM model like LLaMA, you then want to pick a late fusion model because you're just going to be adding a little bit to the end to encourage your galaxies, right? So the bulk of the compute is already spent by Meta or whichever company again is modeled from, and you're just adding a little bit to yourself. So there's trade-offs, and we're going to be talking about a little bit about either of them now. So yeah, just to remind everyone, it doesn't matter which part, you end up with a multimodal destination with around the same compute budget. So, any questions up to this point? Okay. So this is going to be a little bit about a late fusion model with LLaVA. So LLaVA is a way to give image knowledge to an LLM. And all it is you have a clip encoder, which is a neural network for taking images. It's already aligned with text representations because it's been trained in a self-supervised way to align the text and images together in the clip model. And then you add on a little MLP, pass it into a language model, say Vicuna or LLaMA, whichever one your favorite one is. And you do some fine tuning with a bunch of your text so that you fine tune the MLP alongside the text. So the Vicuna model is learning how to align these together. And if you do that for long enough, then the language model learns that you've taken these image tokens and it's produced, and then it knows what to reply to. So you can just, after you do the fine tuning, you can pass in a previously unseen image and it knows what to say. Yeah.
And the clip encoder is totally frozen in this case.
The clip is frozen, the MLP is live, and the Vicuna model is live. Yeah. And the tokenizer for the text is also frozen. So this is why it's late fusion, because you've got two frozen inputs, you're just connecting all the latent spaces together and hoping they line up, and it turns out they do, which is really cool. So this is an example of a late fusion model in astronomy now. This is some work I did with Giraffe, who was at ANU, and now he's in industry, but he's still working on AstroLLaVA. We saw the lava paper and we're like, can we like make one of these for astronomy with astro data? So can we make a big astro data set of galaxies and other astro images, align them with text, and pass them into a LLaVA model? And it's was Giraffe plugged in. It turns out you can, but first you need to make the data set, right? So we made a 30,000 image caption pair data set from Astronomy Picture of the Day images, scraped ESO and Hubble Space Telescope images as well from the websites. We just scraped a bunch of them, got the captions alongside them, and then passed the captions into a GPT-4 model and said, make a question and answer pair data set of this so that we can train a LLaVA model. This is on Hugging Face, by the way. You can just download this, and I think it's quite a nice data set, because I don't know there's many astronomy data sets that have images and text together that you can use to then fine tune a model. So yeah, we took this, we trained a AstroLLaVA from a LLaMA 7 billion parameter model, which is fine tuning. So we fine tuned the MLP to take in the images and then did all the back propagation and all of this just so that we got the model working. And it turns out it works, but it doesn't work excellently. Like, we're getting results that are better than the original models, which is good news. But we were thinking maybe it's because this data that we had was mostly outreach data more than scientific data. And we were testing on a scientific question, which is how well can you diagnose what these galaxies are? How well can you classify them? So we took the Galaxy 10 decals data set, took a bunch of words describing each galaxy, and then asked our AstroLLaVA and our LLaVA models to describe the galaxies in their own words. And it compared the cosine distance of the embedding spaces of these two different data sets. And that's where we got that number. But if you then ask a language model to describe a galaxy in the style of a Galaxy Zoo, citizen scientists, or you have a bunch of Galaxy Zoo citizen science data, you can imagine you can train a much more useful model in this way. And that's what we're going to be doing next. So if you guys are interested in helping out with this, let me know. So that is AstroLLaVA. What time do I have? I've got loads of time. Any questions on AstroLLaVA?
So what would be the application of a system like this in astronomy? Is that something that you could just present an image and then ask questions directly about the image, right?
Well, images, but also if you can figure out a way to pass in X-ray data with text describing the X-ray data and then code it into two different branches into the LLaMA model, it would then be X-ray data aware or spectra or whichever modality you can get it. And this is what we want to try next. So we want to see if we can just pass in any exotic astro modality. And the model would be aware of this, which is what we can't currently do as we know with the AstroMine guys. We can't currently do this with a standard LLM. So this would be a way to be able to do that. You just need to make the data set, which is the tricky bit, but like, it's doable. So I'll talk a little bit about AstroPT now. And this is a family of GPT-like large observation models. And it's super simple. They're just trying to predict the next chunk in a sequence of chunks. You can imagine you pass in a galaxy, you split it up into little windows of 16 by 16 pixel patches. And all it's trying to do is predict the next patch in a sequence of patches going out, spiraling from the center. And in doing this, it needs to learn something about galaxies, right? It needs to know like, oh, the physics in the center is this, so therefore I need to predict the physics on the outside in this certain way. It needs to learn something representational of the galaxy. And the cool thing about this way of doing it, though, I think, is that because it's so simple, you can just chain all your modalities together. So you can have the galaxy images going around, and then you pass in a spectra straight after. You can just keep passing in data in this way. You don't have to really think about how to chain these multi-modes together like you would do with a late fusion model. There's other reasons to pick a GPT. So there's really one social and two technical reasons that I picked to train a GPT here. And I've had a hunch for a long time that the neural architecture doesn't really matter as long as it's appropriate for your task and it scales well. So if that's the case, why not just pick the most popular architecture that everyone's working on? Because lots of people are understanding it, lots of people are contributing to this architecture, making it work better, and we can also contribute back with our special astro knowledge and our special knowledge of how these things can work in astronomy and Earth observation and other areas. Like it's just beneficial for the community if we can get that flywheel going of open source and open science. And if we use a generative loss, which the next token prediction is, we don't need to impose as much of our knowledge on the network. We can just say predict the next token, and doing it in this way, you need to learn something about the physics of the galaxy. There's a data set of 8.6 million galaxy images on Hugging Face. It's around a terabyte, but you can stream it as well, so you don't have to download it all. It's got it's got 8.6 million galaxy images. It's got all of the metadata that go alongside these. It's got a bunch of embeddings now of the different AstroPT models from 10 million parameters to 850 million parameters. So if you want to play around with the embeddings, you can do this too. And we trained a bunch of AstroPTs on this to see if they scale like a text model. And they do, to an extent. So on the y-axis, you've got the validation loss. On the x-axis, you've got the amount of exaflops of compute spent to pre-train the model. And you can see we're following a log scaling law. And I've got another plot at the end to show you as well, which is some new results. We find structure in the embedding spaces. So we asked it a bunch of questions about different topics by probing the latent space with a linear probe. So we just take the embedding space. We do a linear projection to each of these properties, the magnitude, to color, to a bunch of galaxy zoo questions as well of morphology. And you can see here that this is a PCA projection, so there is structure in the embedding space. And there's two islands because there's two different instruments that we're looking at, the North Hemisphere and the South Hemisphere. That's why there's two different islands there. Downstream tasks improve the size as well, which is quite cool. So again, we just probed the embedding space, we compared the performance for all of these different tasks. And the thing I found really cool here is you can see on the bottom left, the stellar magnitude, it suddenly works better, right? So this is an emergent property that AstroPT picks up at a certain size, which is something you also see in LLMs. So I just found it super cool that it has these properties that maybe you wouldn't expect to translate over to a different modality. Newish results. So newish as of July. I took the galaxies dataset that I just showed you. I zoomed in to 256 by 256 pixels cropped, so the galaxies are taking up most of the image. And the scaling continues past 100 million parameters where before it's saturated. So you just need high quality data. You need enough of it. You need a high signal to noise, and the scaling continues, which is quite nice. So that's AstroPT. It's open source. Contributions are welcome. If you want a sticker, there's some stickers on the table as well. And we have loads of time, so I can talk about the Platonic universe as well. But if anyone has any questions about AstroPT, yep.
So I'm assuming that you trained this from scratch specifically.
Yes.
Do you think that you could save compute by fine tuning the regular, like a regular one that's trained on like general images
Yeah.
or something?
That's what I'm trying now. So
Okay.
I'm trying with LLMs.
Yep.
So can you take an LLM, fine tune it
Mhm.
on this, and does it help at all? Like even if it's only seen text, because if you've got
Yeah.
30 billion parameter LLM, maybe starting from that is cheaper computationally than training right from scratch.
Mhm.
Preliminary results look good, but I just need more time
Yeah.
to be able to do.
One of your early parts you showed, early fusion versus late fusion.
Yeah.
And you also have mixture of experts doing better than all embedders.
It does, yeah,
It does.
it does.
So why not?
I haven't tried it, but in their paper they say it does. Yeah, so it's something to watch. Yeah. I haven't seen anyone follow up on that paper. It came out in like this summer, so like May, June. So you'd expect maybe some MOE mixture of experts this neuro cycle. So maybe it's one to watch out for if you're going around the posters. Okay, so final stint now. Can we take any data, any model, and do they converge to the same representation? And this is maybe a provocative thing to ask, but I'll just go into it and see what you guys think. So you might have seen this position paper, ICML, the Platonic universe. And basically what it's saying is if you have two large neural networks looking at different modalities of the same object, so you have, say, an image neural network looking at a tree and a LLM neural network reading a description of a tree, and you take the embeddings out from these, do they produce similar embedding spaces across all of this? And the original paper found that they do to an extent, which is quite interesting. And as the models get bigger, the embedding spaces get more similar. And astronomy is a good test case for this because a lot of astro is multimodal, right? So we've got a galaxy view by JWST, HSC, legacy survey, spectra from DESI. So we could try this on astro. This is what we were thinking. So we used the Multimodal Universe, which is a big collaboration between many researchers, making a big multimodal data set of around 100 terabytes of data from different astronomical modalities. We can cross-match these easily in the Multimodal Universe as well. So you can make the data sets that we need to test the PRH in astronomy. So we made a bunch of paired data. And we're thinking to test this, you can do cross-modal matching, right? So you can have two different models, two different VICs. I haven't seen any astronomy before. It's just two different vision models. Feed them two different galaxy image data sets that are cross-paired and compare the embedding spaces that come out of this spirometry. And we tested this with mutual k-nearest neighbors. So it's just the mutual makeup of the embedding spaces on this. And if, as the models get bigger, they get more similar embedding spaces, we know that PRH is holding it.
Are you doing that only with image data so far?
With Spectra too, and
Spectra.
it works for Spectra as well. I'll show you a cool graph in a minute. you can do this with the same family as well. So you can have a small model, medium model compared to a medium model, big model, and you would expect the graph to go up. Again, this is on Hugging Face, so you can download them all and try it out. This is the cool graph. So the way to read this is we have the foundation model on the x-axis. On the y-axis, we have the different modalities. This is the null case. This is just randomized. So you would expect a trend there. And we find a statistically significant trend across the modes. And this is what we submitted to the ML in Physical Sciences conference, and it was accepted, which is nice. The DESI is spectra. So we see a trend still in spectra. So it's not just image comparisons. We also see spectra getting more similar embeddings to the images as the models get larger, which I found very cool. Most of these haven't seen astronomy, by the way. Only AstroPT has seen galaxies and be pre-trained completely on galaxies. The rest have not seen astronomy data. So it's interesting that they're still finding convergence. And this is a range of different ways to train models. So you've got the standard convolutional network, you've got DynaV2, VIT, and iJetper, and they're just trained in completely different ways to see if this holds across all of these different ways to train a model. So that's the current results. We are finding some new results recently. I'll just flip through one or two.
So how do you interpret the change in trend in some of these plots, like with the VIT and legacy survey, it goes down after a certain number of parameters?
It does, and that's strange. So what I would like to do is train on more models, more larger models, to see if this is just noise or there's something real there. What would be really interesting is finding models that don't follow this trend, figuring out why. Like, are they missing something? Is there something architecturally wrong about them? And this is the way that astronomy, I think, can give back to LLM world, to neural network world, and something that we can uniquely do in astronomy.
So what we're saying here is the similarity between.
It's a similarity between embedded spaces, yeah. On the y-axis, yeah. So y-axis is a similarity. X-axis is model size in millions of grams. But the model size is just a proxy for performance.
Shouldn't the gray one be flat all the time?
If you look at well, it should be flat, but we only went to 2 decimal points, so there's some noise there. Yeah, but yeah, I would like more points so that we can actually be like, yeah, this is something real. This is still preliminary, but it's interesting that we found something, I think. Yeah, so I'll just show on the slide one case where it doesn't work. This is something that Sashrat said on the Discord. He found that a small VLM doesn't follow this trend, which I think is very cool. So suggesting there's something about the way that this vision language model is taking in the data that causes some information loss. And I think it's probably to do with the linear change, the linear step between the clip encoder and the LLM, as we saw with the AstroLLaVA earlier. I think maybe there's a better way to do that, and this is something we discovered from this AstroLLaVA. Same thing here. So they're figuring out, do we need something linear to go on? But anyway, that's the Platonic universe, and that's the end of my presentation. So please let me know if anyone has any questions. If you're interested in helping out with any of these projects, just let me know. We're looking for hands. Yeah, thank you.
Thank you, Mike. Good stuff. Any questions for Mike? Yeah, Phil.
So these 3 different approaches, what do you see as like the future of building a foundational model astronomy? Like, which path should we go down? You know,
I think we combine them. So like you said, if we can take an LLM and make it astronomy aware, we can skip the entire step of us pre-training the model. We can also skip all of the architectural difficulties of the early fusion models. And I think that's probably the way to go. If we take an LLM in the center and then fine tune it so that it's astronomy aware of these modalities, I think it's probably the best approach.
and that's just because we can take advantage of OpenAI's training.
Exactly. If someone spent millions of hours to compute, we should use it. I think. Yeah.
In fact, you are working with Sogol on this project.
Yeah.
Where you're trying different tokenizers for the astronomical data to project it into space that a transformer can understand. But that transformer can be replaced by a large language model and then see whether it can, do the same things that the specific transformer can do.
Yeah.
As long as you can project the astro data into the LLM space, which is simple.
And trying to do the same things cheaper than retrain it from scratch as well. So we don't, like, it doesn't have to be cheaper overall, but cheaper for us as astronomers, maybe.
Yep.
Yeah.
And, yeah. How do you see that going? Would you leave all the weights over then train the entire model, or would you freeze the?
I've been doing low fine tuning with, I found it's unstable at 256 alpha. So you need less than that. But I wouldn't train end to end or fine tune end to end because it's going to forget a lot of stuff that is built up as knowledge from the text data sets that it's seeing. So there's some kind of balance there.
One final question, Mike, comments?
Yes, yeah.
Can you say a bit more about times?
Yeah, like how you would pass time series into with the GPT model.
The other thing is the body you made an instance sparse with
Yeah. So, let's go back. For the time series, what I would probably do, it depends on exactly what your time series data set looks like, of course, but if it's dense, I would just chunk it out like this and pass it in as a sequence, trying to do the next chunk of time series. If it's sparse, I'll probably have a single data point input with the timestamp passed in as one thing, and ask it to predict the data point at timestamp t afterwards. And then you wouldn't have to have everything in order. You could just say predict the time at this time, and it would need to learn again something about the physical time series to be able to do this.
Since you're in this,
Yeah.
quickly, like, how are there any differences in performance depending on how small or big the patches are with respect to the underlying structure of the galaxy? So if you were going to make those patches even smaller, would that be a good idea because it understands better like
Yeah.
small structures in the spiral arms and things like
That's
that?
true. Ideally, you would have a single pixel patch, but because attention is expensive and it's scaled and squared, you have to patch up like this. So it's a trade-off. But ideally, you would just have a pixel patch and you predict each pixel in a row. But we have to chunk it because otherwise we can't train these models.
But in general, you would say the smaller the patch, the better.
I would say so.
Yeah, same line of questioning. Does it actually matter that you have a spiral shape patching? Or if you just do it in a grid?
I did it for practical reasons, so we can have different sized galaxies going in.
Yeah.
You could probably do it in a grid, and I did it with a grid with the Aeon tokenizer. It's just
Like this obviously feels more intuitive, but it doesn't matter.
it doesn't. The model doesn't care. I don't think. But if you want to pass in a galaxy of 256 and it's always centered, maybe it's easier to just assume it's centered and spiral out from the inside.
So it's not because it's a spiral galaxy that.
No,
So if you go in the other sense, it's not gonna make a difference.
that'd be cool. We could do one way and then do with one. Yeah.
Cool.
Yeah.
All right, well, Mike's also local to us, so come talk to him. He's in the second floor over there, so come see him if you have more questions, and thank you very much. See you next week. Thank you.